Hello, I'm happy to welcome you all to this lecture series on process heat transfer. In today's lecture series, we are going to look into the design calculation for a double pipe heat exchanger. Basically, a heat exchanger is a device that transfers heat between two fluids, one of which will be a hot fluid and another one will be a cold fluid. So, double pipe heat exchanger basically consists of an inner tube and an outer tube. For example, if the hot fluid is going inside the inner tube, the cold fluid will be flowing in the annular space between the inner tube and the outer tube. So, in general, the heat transfer rate equation is given by Q is equal to U into A into delta T LMTD, where U is the overall heat transfer coefficient and A is the area of heat transfer and delta T LMTD is the logarithmic mean temperature difference. If you look into the slide, I would have given UD instead of U. The reason is because any fluid that is going inside the the tube or the pipe, it is going to give you certain resistance, so which is basically because of fouling or dirt factor. So it is important to take into account of this resistance while calculating the overall heat transfer coefficient. So before getting into the design calculation of a double pipe heat exchanger, it is important to know the process conditions and physical parameters of the hot and the cold fluid. For example, the hot and the cold fluids inlet and outlet temperature and physical properties like thermal conductivity, specific heat capacity, viscosity, density are very important. And also, this double pipe heat exchanger consists of an inner tube and an outer tube. And so, the inner diameter and outer diameter of both the inner tube and the outer tubes are required, and sometimes the pressure drop is also required. So the first step in the design calculation involves the calculation of heat transfer rate, that is the Q. We know that the heat that is lost by the hot fluid is actually gained by the cold fluid. So the MCP delta T of the hot fluid should be equal to the MCP delta T of the cold fluid. This equation can be used in cases where one of the temperature of the hot fluid or cold fluid is unknown, and also, for example, the mass flow rate of hot fluid is given and the mass flow rate of cold fluid is not given. In such cases, when any one of the parameters in this equation is not known, this equation can be used to find out. So the next step is to find out the logarithmic mean temperature difference, that is delta T LMTD. This value highly depends on the type of flow. For example, if we consider the double pipe heat exchanger, if both the hot and cold fluid are going to enter into the double pipe heat exchanger in the same direction, then we call it as a parallel flow or a co-current flow. On the other hand, if the hot fluid and the cold fluid are going to enter into the double pipe heat exchanger in the opposite directions, then we call it as a counter current flow. So this delta T LMTD value highly depends on the type of the flow. For example, if we consider co-current, then delta T1 is given by hot fluid inlet temperature minus the cold fluid inlet temperature. Why? Because both the fluids are entering into the heat exchanger in the same direction. And also delta T2 is given by hot fluids outlet temperature minus cold fluids outlet temperature. On the other hand, if we look into the countercurrent flow, then the delta T1 will be given by hot fluids inlet temperature minus cold fluids outlet temperature, and delta T2 will be given by hot fluids outlet temperature minus cold fluids inlet temperature. So it is important to know this difference in delta T1 and delta T2 when compared to that of the co-current flow and the countercurrent flow. So the next step involves calculating the area. So from this step onwards, let us divide this design calculation into inner pipe and the annular space. So the first thing is, one of the fluid is going to flow into the inner tube and another fluid is going to flow in the annular space between the inner pipe and the outer pipe. So let us divide this calculation in such this way. So first, let's take into the inner pipe. The area calculation will be given by area is equal to pi by 4 into di squared. You remember, the fluid is flowing in the inner pipe. So inner diameter of the inner pipe is going to be in contact with the fluid. That is the reason why we are taking the diameter of the inner pipe, and also the inner diameter is considered here. So from this Next step is to find out the Reynolds number followed by the Prandtl number. Why? Because we know that Q is equal to U into A into delta T LMTD. So when you want to calculate this overall heat transfer coefficient U, it is important to find out the individual heat transfer coefficients of the inner tube and also the annular space. So first we are calculating the inner tube. So we have to calculate this HI for the inner tube. That is heat transfer coefficient for the inner tube we have to calculate. So basically, when we want to find out the heat transfer coefficient for any fluid flowing in the pipe, we'll be going for either Cedar-Tatti equation or Dittus-Boelter equation. So this usage highly depends on the values of Reynolds number and Prandtl number. So it is important to find out this Reynolds number and Prandtl number. And one more important step to be noted is that in most cases in your problem or in the design calculation, velocity of the fluid will not be known. So in this case, the mass velocity of the fluid will be given in your problem. So we can find out the velocity through this mass velocity by using this formula, mass flow rate divided by area. And it's very important to note that here the area, the diameter we are going to use for the calculation of area is inner diameter of the inner tube. Followed by the next steps like NRE and NPR are very common, just like our usual thing. So NPR is given by Cp mu by K. Here Cp is the specific heat capacity of the fluid flowing in the inner tube, followed by viscosity of the fluid flowing in the inner pipe and thermal conductivity of the fluid flowing in the inner pipe. So basically based on these two values, we can determine whether we are going for Cedar-Tatti equation or Dittus-Boelter equation. I have given you one example of Dittus-Boelter equation. We know that it is given by Hd by K is equal to 0.023 into Reynolds number power 0.8 into NPR, that is the Prandtl number power A. But this value of A highly depends on whether the process is a cooling process or heating process. For example, if the process is a heating process, we'll be replacing A with 0.4. On the other hand, if it is a cooling process, we'll be replacing A with 0.3. So through this equation, we can easily find out the heat transfer coefficient HI based on the inner tube. However, when we go for the design calculation, it is important to find out the heat transfer coefficient based on the outer diameter of the inner tube, because the heat will be transferring from the inner pipe to the fluid in the outer pipe, right? That is to the fluid in the annular space between the inner tube and the outer tube or the pipes. So the formula is given by Hi naught is equal to Hi into Di divided by D naught. So through this we have find out the heat transfer coefficient for the inner pipe. So one part of the design calculation is completed. So the next step is to go for the fluid that is flowing in the annular space between the inner tube and the outer tube. So important thing to be noted here is that first the area. So when we go for calculating this mass velocity, that is mass flow rate divided by area, here the area diameter will be given by pi by 4 into d2 square minus d1 square. So what is d2 and d1? d2 is the inner diameter of the outer tube and d1 is the outer diameter of the inner tube. So it is important to replace the diameter accordingly when we go for calculation of heat transfer coefficient in the annular space. Also, another important thing to be noted here is that when we go for the calculation of heat transfer coefficient H naught for the annular space, the diameter in the Nusselt's number part, that is Hd by K, will be replaced with equivalent diameter. Since the fluid is flowing the annular space between the inner tube and the outer tube, it is important to remember it is a non-circular path, and so we have to go for the equivalent diameter. So next, after that, the usual procedures like finding out the Reynolds number and Prandtl number continues. Based on the values of Reynolds number and Prandtl number, we can either go for the Cedar-Tatti equation or Dittus-Boelter equation to find out the value of H naught. That is the heat transfer coefficient for the fluid flowing the annular space between the inner tube and the outer tube. So the next important step is to find out the overall heat transfer coefficient U. So it is given by the 1 by Hi plus 1 by Hi naught. So basically we are going for the heat transfer coefficient of the inner tube and the heat transfer coefficient of the fluid flowing the inner tube and the outer tube. When we add both of this, we'll be getting a overall heat transfer coefficient in terms of clean factor. But we should also include the concept of dirt or resistance, and that is the reason why we are adding RD, the resistance, also into the equation. So when we add that, the UC will actually become into UD. And we know that the overall heat transfer coefficient is given by UD instead of UC, because it is important to take into account of the dirt or the fouling that is given by any type of fluid. Since we have calculated delta T LMTD and also UD, and area of the pipe is given by pi d naught into L. When all these formulas are known, we can find the heat transfer rate Q for a double pipe heat exchanger. So let us capture all this into a short 1 minute thing. So for a double pipe heat exchanger, when you want to find out the heat transfer rate Q, the formula is given by UD into A into delta T LMTD. Whereas UD is the overall heat transfer coefficient, A is the area of heat transfer, delta T LMTD is the logarithmic mean temperature difference. So let us divide this design calculation into two parts, whereas one is the inner pipe and another one is the fluid flowing in the annular space in the inner pipe and the outer pipe. So there is going to be two major difference, that is especially lies in the usage of diameter. When we are going for diameter calculation of the inner pipe, here it is important to know that for the area calculation we'll be using inner diameter of the inner pipe. On the other hand, when we go for the annular space, for the area calculation, the diameter we are going to use is outer diameter of the inner tube and the inner diameter of the outer tube, d2 square minus d1 square, whereas d2 is inner diameter of your outer tube and d1 is the outer diameter of your inner tube. And another important thing is the d value, that is we are going to use when we consider the annular space between the inner tube and the outer tube. Here it is important to know that is the non-circular path, and hence by using the equivalent diameter. Then the normal Reynolds number and Prandtl number calculation continues, based on which we'll be using the Cedar-Tatti equation or Dittus-Boelter equation to find out the heat transfer coefficient values. Based on the heat transfer coefficient values, we'll be calculating the overall heat transfer coefficient, and addition of resistance to the overall heat transfer coefficient, UC will become UD. And the final equation is given by heat transfer rate Q is equal to UD into area of heat transfer pi d naught into L into the delta T LMTD. Thank you for watching this video. In the next video, we'll be dealing with the design calculation for a shell anti heat exchanger. If you have any doubts, please put it in the comment section. Thank you for watching. Thank you.